Sora 2's some black magic. Type in the most random stuff, and you get a crazy realistic video.
Your chicken's looking nice, pal.
Woo! Yo, he stole my chicken!
Got a crispy treasure, can't slow me down. Hot and golden, I'm out of this town. Move, move, Friday, victory.
Well, get back here.
Run, spin, slide, I'm gliding out the door. Fried love in my arms, can't give it up no more. Hey!
And you're telling me this is all just math? Well, kind of. Let's start from the bottom. The AI is trained in 2 steps. In the forward process, the model takes a clean image, or in this case, a clean video frame, and deliberately ruins it. It systematically adds what's called Gaussian noise. Think of it as digital static over hundreds of tiny steps. The original video data is totally buried. Now here's the magic. The reverse process. The model has spent its life learning how to perfectly reverse every single one of those hundreds of steps. The goal is to take that pure static and, step by step, precisely predict and remove the exact amount of noise to reveal the frame underneath. If the model does this perfectly across all its training data, then when we give it a brand new noise-filled canvas, it can start denoising that canvas until it resolves into exactly what we asked for. That's the core engine, learning to turn noise into signal. But here's the ultimate problem. Video files are massive. A 20-second 1080p video is billions of pixels. You can't just feed that raw data into an AI. The computational cost would be astronomical. This is where Sora 2 uses something called a variational autoencoder, or VAE. The VAE is basically a highly trained digital compressor. The VAE's encoder takes your massive video file, the blue side, and compresses it into a tiny, efficient version called latent space, the yellow middle. That's the basic diffusion model. But Sora 2 doesn't just use any diffusion model, it uses a turbocharged version called the diffusing transformer, or DIT. This compressed information is the essence of the video. The decoder then uses that latent information to expand the video back out when it's finished. Once the video is compressed, Sora needs to break it down into units the AI can actually process. Here's how. The model first takes that compressed data and breaks it down into what are called space-time patches. Think of it like cutting a video into tiny cubes. Each cube contains a small piece of space and a small slice of time, a 3D grid of pixels across frames. Sora then treats this sequence of patches exactly like words in a sentence. Speaking of breaking down pieces together to build a full experience, today's video is brought to you by Mobbin, the ultimate design inspiration platform for creators like you. Imagine having access to over 500,000 real-world app screens and 80,000 user flows from 1,200 industry-leading apps all at your fingertips. That's Mobbin. And I have a 20% discount for it just for you. Forget sifting through conceptual designs or manually taking screenshots for hours. Mobbin empowers you to find highly relevant design references in seconds. Whether you're benchmarking competitors, researching UI patterns, or staying up to date with the latest trends, Mobbin has you covered. With powerful features like NLP search, visual search, and text in screenshot search, you can find exactly what you need, when you need it. And with their Figma plugin, you can export screens directly into your workspace. From freelancers to enterprise teams, Mobbin offers plans to suit every need. Join over 870,000 designers worldwide who are using Mobbin to create great digital experiences faster and smarter. Check out Mobbin today and elevate your design game. Links in the description below. Now back to the video. For years, diffusion models used something called U-Net architecture. U-Nets are convolutional neural networks shaped like, well, a U. They compress information down, then expand it back up, which worked great for images. What's the biggest difference, you asked? Well, transformers, the same revolutionary architecture behind ChatGPT, have a superpower. They scale incredibly well. Feed them more data and more computing power, and they just keep getting better. U-Nets don't scale the same way. This is exactly why OpenAI chose the Diffusion Transformer, or DIT, for Sora. The DIT processes those space-time patches with its immense power. This combination of the patch data format and the transformer's ability to scale is why Sora can generate an entire minute of coherent, high-fidelity video. And you can see the power of that scaling in action. The diffusion transformer doesn't denoise the video all at once. It does it over many steps, gradually revealing the scene. Look at this. On the left, you have pure noise. In the middle, the model has completed a few dozen denoising steps, and the scene is just starting to resolve. On the right, after hundreds of steps, the final photorealistic image emerges. The diffusion transformer doesn't denoise the video all at once, it does it over many steps, gradually revealing the scene. Now here it is with the 4x the compute. The detail and coherence jump noticeably. And finally, the model trained with the 32x the compute. This progression proves the DIT's power to resolve pure noise into a stable, high-fidelity scene. This controlled step-by-step resolution, guided by the DIT's powerful attention, is what gives Sora videos their fluid motion and stable structure. But how does it know what to generate from your prompt? How does it know that when you type a robot, you will get a robot and not just something else? Well, Sora 2 converts your text prompt, a robot in a future setting, into a mathematical representation called an embedding. These embeddings are injected into the diffusion transformer through cross-attention layers. At each denoising step, the transformer is asking, given this noisy video patch and this text prompt, what should the clean version look like? This mechanism lets every visual patch look at the description and adjust accordingly. But the guidance goes deeper. To accurately follow a user's prompt, Sora uses the recaptioning technique from DALL-E 3. It first trains a highly descriptive captioner model to produce detailed text captions for all its training videos. Even better, it uses GPT to turn short user prompts, like a toy robot, into longer, detailed captions before it ever starts generating. This is how Sora follows complex instructions for characters, settings, and styles so precisely. What's particularly impressive is its instruction following. It doesn't just understand objects, it understands camera movements, physics, and style. This is why the final video is so cinematic. Now here's a huge leap. Synchronized audio generation. Sora 2 generates sound effects and can even produce dialogue that matches lip movements. A separate audio diffusion model analyzes the visual content. It can be a door closing, footsteps, or someone speaking, and generates audio that matches the visuals frame by frame. None of this works without massive amounts of training data. The physics simulation capabilities, accurate motion, and proper object interactions emerge entirely from the DIT having seen so much video that it's learned the implicit rules of how the world works. Now let's look at how that massive scale translates into the final cinematic video. Sora 2 is designed to be a true generalist. Past models always required videos to be cropped or resized to a standard square format, like 256 by 256. Sora bypassed this by training on data at its native size. This means you can prompt Sora for a vertical 1080 by 1920 video for a phone, a widescreen 1920 by 1080p for YouTube, or anything in between. Furthermore, training on native aspect ratios results in improved framing and composition. Sora avoids the common problem where a subject is only partially in view, giving better shots right out of the box. To accurately follow a user's prompt, Sora uses the recaptioning technique from DALL-E 3. It first trains a highly descriptive captioner model to produce detailed text captions for all its training videos. Finally, Sora is not limited to text. It can be prompted with other inputs, such as pre-existing images or video. This capability enables it to perform a wide range of editing tasks. So that's how it all comes together. The prompt is encoded, the diffusion transformer denoises the latent patches over hundreds of steps, the VAE decodes the final image, and the audio model layers the sound. Sounds complicated? Not really. We've been doing it with images for decades now.